everyone. So I'm very pleased to be here today and to talk to you about nonlinear nanocrystal for electro-optic and quantum devices. So let me first thank the people of my team for the work I will present today. And what we do, we are really focusing on the integration of quadratic material. So on this first slide, what you could see is a metal lens made out of barium titanate, and I will show you how we do this kind of lenses in the second part of the talk. But first of all, I would like to argue why we want to miniaturize quadratic optical material. First of all, it's for data transport. So we all know the long haul network over fibers works fine. It might be saturated at some point, but it's also the short haul optical, the short haul networks. So what about those data centers? So if they want to switch from the electrical interconnect to optical interconnect, because currently the electronics based on semiconductors like silicon is much more compact than photonics, but is really reaching some limit in terms of data transmission and even on short distance in power consumption that escape in thermal losses. So we're wondering if there is a material out there that could be used for small footprint, optical interconnect with high yields, low power consumption, fast speed, and low losses. And we're even thinking of using this material for spaceborne application. Therefore, they need to be really lightweight and robust. The data transmission is not the only application, or the application are for sensing. So there are photonics material that could be suited for monitoring air in a closed or open environment, or your heart beat or liquid, as in those pipes in the industry. So you really need integrated spectrometer for that. And other application would be quantum computing. So here you have an example of a tabletop experiment where quantum computational advantage was demonstrated, but for generating a few tens of photons, you will need sources that are really big and not even on that part of the experiment. So the idea is to find out a material platform and which one would be able, for instance, to do the photon pairs generation on a chip. And current technology, they're really relying on centrosymmetric materials, still on silicon electronics for certain photon emission on diamonds that are mainly centrosymmetric material. But the material I will talk about today, they are mainly non-centrosymmetric material. For instance, barium titanate, BaTiO3, lithium niobate, LeNBO3, as well as a few 3,5 nanowires material. The interest of those materials, especially barium titanate and lithium niobate, is that they are transparent over a very broad spectrum, from the near UV, so 350 nanometer, up to the mid-IR, 4 micron. So we have really a wide range of wavelengths you can work with. The versatile electrical and optical property we're interested in are, first of all, typically in those non-centrosymmetric material is second harmonic generation, because the Chi2 tensor that is intrinsically defined for the material, for instance, here is the Chi2 tensor of lithium niobate, where this D33 parameter is pretty strong. It's about 30 picometer per volt, is actually only non-zero in non-centrosymmetric material. And here you see the quadratic dependency of the polarization, with the factor being this Chi2 tensor. Other effect I'll talk about a lot at the beginning of the talk is electro-optic effect. So we also want to exploit those effects, especially for making the modulators that I was talking about for data transmission. And it also has a tensor that is different usually from the second harmonic generation tensor. There's a relationship between the two, but the values are different, especially for barium titanate. So that's why we are interested in this material. There are components could be really strong, one order of magnitude stronger in bulk than lithium niobate. So which material you will pick for either an optical experiment or an electro-optic experiment will matter, as well as for spontaneous parametric down conversion. And that's the third property I will talk about towards the end of the talk, how we can generate pair of photons starting from a frequency of 2 omega. For instance, we work at telecom wavelengths. So here we will start with 780 nanometer and generate a signal and idler photons at the frequency typically around 1550 nanometer. This is not so well defined, but we are just looking at the entanglement between those two photons that are generated through this process. Now, which kind of fabrication we are doing and how small those Ki2 material can be. They're well known as bulk since the discovery of the laser, so 60s, 70s, they're used since then. People have developed a titanium diffuse process where you can do waveguides inside a bulk material of a few hundreds of micron thicknesses. But since a decade or so, a bit more, there are thin film lithium niobate on top of a box layer, so similar as the SOI, but for optics here, where you have this isolating layer and on top of a thick silicon wafer. And therefore, since now less than a decade, we have all those photonic chips that can be done out of this electro-optic material that is lithium niobate. I will show you the first part of my talk about those top-down fabrication of lithium niobate on insulator samples. And the second part of the talk, I will also talk about bottom-up fabrication because we are struggling a lot with top-down fabrication. Lithium niobate is an oxide, so there is no wet etching possible as you can do with silicon along very specific crystalline orientation. Therefore, you have to work a lot to get the structure you want. And we started being interested in also working with nanoparticles that you really can get by hydrothermal process or molten salt synthesis process, how to nano imprint them, as well as sol gel, because there you really start with a smooth material, though both they are really polycrystalline. So you will not get a monocrystalline layer, but some polycrystalline layer, but that I will show you, they're also still powerful and show many of the properties that I was talking about before. And there are also interesting work currently on polymers, electro-optic polymer that are have much higher tensor component as lithium niobate, for instance. It could be the component I was showing you before in the tensor up to 1000 picometer per volt, which is super interesting for having efficient electro-optic modulation. So let me start with the demanding top-down process that we want to master so that we can realize small devices. And when I talk about small devices, here I compare a bulk crystal lithium niobate, and you see the cross-section of a waveguide here. You have the vertical position where you will launch the light, for instance, with this fiber. And yeah, you see that the waveguide will be elongated in the plane of the screen. What is striking between the material we are having now, thin film on the oxide, is this cross section. The mode area in the bulk material that can be achieved with titanium indifused is about 1 order of magnitude, so 30 even more micron square, as compared to the mode area that we can achieve with etching lithium niobate on top of the silicon dioxide. Here you see a mode area of 1 micron, and therefore this was the key parameter to obtain modulator that were working up to 100 gigabit per second. Contrary to this kind of technology, where the typical modulator will reach 10 gigabit per second at this point, and experimentally, maybe in the labs, but not really commercially, 40 gigabit per second. So you see how you can increase the rate here. And the challenge in the fabrication of, first of all, you have to get these thin films. Now they are commercially available. The commercial process is ion implantation, then wafer bonding and heating, which is called ion slicing or smart cuts. And we have currently a European project where we are developing the lithium niobate on insulator PIC platform for having also substrate that can be commercially available in Europe. And the second challenge, as I was telling you before, is to make this tiny structure. So we usually use E-beam exposure, dry etching, so with ICP, and afterwards you have the metallization so that you can deposit the electrode very close by to your waveguide. So here you don't see the electrode, you just see the waveguides. But on the next slide, Here you have our early fabrication steps where the electrodes were a bit detached, the walls were not so smooth. Here what you see is a nano waveguide with some features that can be used as gratings, so Bragg gratings along the waveguides. And here you see the striking improvement of the fabrication over the years, where the gold is not so smooth because it's sputtered, but the lithium niobate is very smooth. So this is done by ICP etching and E-beam, so that you can see you have a Bragg grating. And what can you do with a Bragg grating? You can do a modulator. So there are people doing modulator with plasmonics and the electro-optic polymer I was showing you before. Then the modulator are really tiny, but the electro-optic polymer cannot be, it just deposited and it cannot be etched or prepared in such a way that you can structure it. Then the typical modulator, they are lithium niobate on lithium niobate on insulator or Mach-Zehnder configuration, the same as in the bulk. In Mach-Zehnder configuration, you split the light into two arms and you induce a phase change by applying an electric field to one of the arms in a push-pull configuration, for instance. And here what you can see, we were doing a modulation using a Bragg reflector. So in that case, you don't have a phase change along the waveguide, or you will induce a phase change along the waveguide. But first of all, you have stop band, which is induced by the Bragg grating that you have here. So we'll have partially reflection due to the fact that you have alternating layer of lithium niobate and air. And by improving the fabrication, so you see this is the 12 dB stop band that we are having with that kind of design. And now we have a 35 dB stop band with a perfect design, or let's say much more perfect design. And what we are using to do the modulation is the steepest part of this stop band here. And by applying the electric field, you can really move slightly the steepest part and define your zeros and ones along the different optical path lengths here. And when the zeros and ones, they are well defined, it means they are very low beta error rate, this eye stays open, so white in the middle, so that you can really well define when you send random zeros or random lines of ones. They go from 0 to 1 or 1 to 0 without having too much crosstalk here. And this kind of eye diagram was taken as 100 gigabit per second with a beta error rate of 10 to minus 5. Okay, so this is what we can do with this lithium niobate on insulator platform, electro-optic modulator, but also thermo-optic modulator. Why we were interested in thermo-optic modulator is, as you can see, the waveguides are really tiny. And there's quite some error that can occur during the fabrication. And if you have one more knob to tune, for instance, a resonant wavelength by thermal means, so it's not as fast as electro-optic. So you see thermo-optic is on the order of 1 to 100, 1 to 10 kilohertz, let's say a few hertz to 10 kilohertz. But what you can see is that lithium niobate is also suffering from some shift that you have, some DC drift that you have when you apply an electric field. But when you use a thermo-optic shift, there is not this drift that may occur. So as you can see here in the electro-optic cases, and then you have much more precise control of the ramping up of the modulation and ramping down. That was one of the motivation. And the other motivation is that now we want to pack all the building block we are able to fabricate on a more complicated chip with different functionalities. For instance, the crossings, the Bragg gratings, also resonator. Here you see evanescent field couplers that we can realize, the phase shifters, thermo-optic. We also have a spectrometer that we can make on a chip. Now we are working on making not a spectrometer with silicon nitride, but also lithium niobate fully etched on a chip, as well as the grating coupler that you would need so that you don't need end-fire coupling, which introduce even more losses than the grating couplers. Okay, this is one part of our research where we are really trying to make those on-chip fiber-coupled and fire-coupled systems, either, for instance, for supercontinuum generation or for those Bragg grating. But what about free space optics, how to make polarizers, lenses, filters, also in UK materials, so that you can take advantage of the electro-optic effect, also free space. And we've been struggling to make metasurface during using lithium niobate insulator, because you need a high aspect ratio, you need fins that are very close to each other. And our first attempt was on the lithium niobate on insulator layers by etching down with E-beam and ICP, as I was showing you before. And here you see the kind of unit cell geometry we were aiming at to obtain a lithium niobate metasurface in order to modulate the phase along this metasurface. Here, the difference from before, the substrate is transparent. We use a lithium niobate substrate and not anymore silicon substrate. So we could really use this as a meta lens or as a transparent metasurface. Though the etching, as you could see already before with the waveguides, we end up having trapezoidal shapes because of the non-selective etching of an oxide. This was good enough to obtain electro-optic metasurfaces. So we were first simulating this kind of trapezoidal shape. Here you can see the optical fields simulation, and you see where you have the strong where you have the strong fields, which is inside the structure, right? It's a dielectric somehow, and here at the edges as well. And if you select the electric field that we are able to apply with the electrodes that are surrounding the metasurfaces, so the metasurfaces, they are typically 20 by 20 micron. So here the electrode, they are much more apart from the structure than for the electro-optic modulator, right? For the electro-optic modulator, we had a sub-micron size waveguide with electrodes that were only 5 micrometer apart, and here they are 30 micrometer apart. So you really have to apply quite some field to be able to change the optical path here. And there are some enhancements, right, at those edges that we can take advantage of to change the refractive index really locally. Here you have first the transmitted signal simulation versus the wavelength, where we are able to change the refractive index locally by applying an electric field on the electrode I was showing you before. So we are working on the dispersive behavior of a metasurface, where we measure the modulation enhancement, which is the modulation amplitude of a metasurface above, let's say, divided with the modulation amplitude on a film where there is no metasurface. So here you see the simulation. So this is the transmitted signal, which has a deep at 776 nanometer, and the simulated modulation signal that is working best at this steep derivation of the simulated transmitted signal, where we'll be able to do this dispersive behavior. This was a simulation with 2-volt peak-to-peak apply, so really low voltage. There were previous work on metasurface applying 600 volt to see anything. But here we're just applying 2 volt, and you see that those are the measurements. We have the transmission here, which has the dedicated deep at well-fitted deep at 776, and the steep modulation enhancement here at the derivation here. What we could measure with this 2-volt peak-to-peak field applied to the metasurface was an enhancement of the signal when we measure off and on the structure of 80 times. So we really have to play with the resonant metasurface to be able to measure an electro-optic modulation with a very low voltage apply, so that it's a voltage that you want to apply on a chip, right? Not 100 volt. Okay, so this was it for the first part of the talk, where I was really focusing on top-down fabrication. If you like, I can pause here, and if you have really already questions about the top-down fabrication type of samples, I'm happy to answer. So I see a question from the first sample of lithium niobate metasurface etching with ion miller rather than RIE or others. So we do argon ions etching, right? We really etch with ion miller. not with rapid or IRE, right? So not sure I answered the question, but we really do argon ion bombardment of the sample for etching. Yes, reactive ion milling. What we have some trials with that, not much experience though. But what we see is a bit more, from what I know, it's a bit more reacting with the surface and maybe not as smooth as what we are having with ICP. But yeah, so we don't have much experience. Okay, question about the thermal optic modulation. If you consider any phase change material like vanadium, germanium. Yeah, so we are also collaborating ourselves. We don't work with phase change material, but we are collaborating on optical measurement with people using phase change material. Though, can you really achieve 10 kilohertz with no DC drift with those phase change material? That's, yeah, I'm not familiar, right, really, to which speed you could achieve modulation. And then also if this is totally reversible over a high number of cycles, right? The material is maybe more sensitive. Okay, any other question? You may say them loud, otherwise I just continue. Did we try to balance between physical and chemical etching to gain more straight wall for lithium metasurface? Yeah, so we have I didn't cite it here. We just have a paper out in the Nanophotonics journal on ICP etching, and actually how it is, how we have to do some chemical etching as well, or let's say wet etching as well, because when we do the ion etching, argon ion bombardments, you have redeposition of amorphous lithium niobate on the walls. And therefore, there's always a wet etching step as well. Though there are some possibility of playing with the mask and the etching to avoid the redeposition. And in this paper, we discuss this possibility. I can post it after my talk in the chat. So it's really a paper from Fabian Kaufmann, Giovanni Finco, and within my group, yeah. Okay, but the straight wall you will never get. There's always an angle. So you will never get 45 degree. You always have an angle due to the non-perfect etching, yeah. Okay, thanks for the question up to now. Now I'm moving to bottom-up fabrication. Actually, since we are struggling so much with this etching, we started working also with nanoparticles, nanowires. First of all, I have quite some paper on single particle measurements, economic generation. But then we started assembling those particles for different purposes, either small particle, barium titanate, or lithium niobate tubes as well. And we also have collaboration of people growing nanowires, because nanowires, they have very high Chi2 coefficient, though they are not birefringent, but you can really profit from Chi2 effect for spontaneous parametric Dan conversion, for instance. And that's the experiment that I will show you today. First of all, why going for those particles? As I said, is to simplify fabrication. There is also the possibility to find out about material that does not exist as high quality crystal. So there's a chance to test new compounds. Also, this is very useful for nonlinear optics. So we are able to relax the phase matching condition with polycrystal. What do I mean with that? So if you start from a single crystalline particle of, let's say, barium titanate, what this arrow is showing is the orientation of the crystal axis. We have some ways of fabricating microspheres through templating, templating assemblies, where the orientation of the crystal axis is not at all controlled. And then what we'll end up with is some kind of microspheres with Chi2 orientation that are totally random. And when Chi2 orientation is totally random, when you apply electric field to the or you apply light to this structure, the question is what happened to the second order signal? And one of the maybe intuitive response would be the second order signal should vanish, right? You have a structure that is made out of particle with totally random oriented crystal axes. But actually, this is not the case. What you see here is a very strong, I would say. So you just need a rather sensitive camera, but you can even see it when you have enough particle with your bare eye. This is a second harmonic generated speckle from a nanoparticle of barium titanate. They are below 50 nanometer, the single grain size. And these particles, we can control the size by doing this template assembly from a few hundred of nanometer up to few tens of microns. And the signal is not zero because we are taking advantage of random quasi-phase matching. I'll talk about phase matching afterwards when I come back to SPDC. But this, what the signal is doing here, even the nonlinear signal, is a random walk. And by a random walk, the net results of the walk is not zero. So you have second order generation with speckles that are really, really strong. This is for second order effect. Second harmonic generation. We are also asking ourselves what happened to the electro-optic effect. So if you apply electrode to this kind of structure, to a structure that you did not orient yet. So here we just spin-coated particles on top of a structure that had plasmonic resonances. And those spin-coated particles between those electrodes, they were showing really strong electro-optic responses. We are estimating the electro-optic responses, the effective refractive, the effective coefficient of the tensor as I was showing you before. And this was about 30 picometer per volt, which is an electro-optic effect responses of material as bulk, such as lithium niobate, even though the material is now scrambled into an effective media because the particles are just spread out onto this structure. So there is a second order effect, there is electro-optic effect. And the last question we're asking ourselves, is there spontaneous parametric down conversion possible in that kind of structure? So why we want to do SPDC? You know, SPDC is one of the leading techniques to generate single photon for quantum computing application. It has, though, material dispersion, right? If you launch your light at, for instance, 780 nanometer, you have a certain crystalline orientation that is indicated here. Your crystal could be above the coherence length of the material. So then what will happen? You will have delta K. You will have a phase mismatch between the wavelength that you are launching into your material and the momentum conservation that has to be kept when you generate the signal and idler out of this K2 material. What happens with the spontaneous parametric down conversion probability? Same as for SSG. If you go above the coherence length, you will have a non-phase match signal, which means when the crystal is really thick, which means that your SPDC probability at some point will totally decay and even be totally annihilated for 2 coherence lengths of your crystal length. On the other hand, if you wouldn't have this phase mismatch, what happens is that the SPDC probability will continuously grow, what is called perfect phase matching. And there are many ways to try to beat this problem of phase matching. For instance, in bulk, you take BBO crystals. You may have seen that kind of setup, and I'll show you afterwards how does it look like in your laboratory. And those BBO crystals are birefringent. They have the nonlinear, the ordinary, and the extraordinary refractive indices that are wavelength dependent. So you can play with the orientation of your crystal. So you just make it a bit tilted so that you match for 2 different wavelengths. So your second harmonic wavelengths or your SPDC wavelengths and the pump wavelengths, the 2 refractive indices. This is a way to do it. And this is what is done when you want to have bulk sources. This is really a standard method. It has been used since decades now to make SPDC sources for the labs. And we, for instance, here is just a picture of that kind of sources in the lab. And here you see the BBO crystal that we can tilt. But that's not what we want, right? We want integrated structure. So what you can play with is quasi-phase matching. In quasi-phase matching, you take a crystal, also bulk, first, but we'll see how we can do it on lithium niobate on insulator. And then you try to invert the orientation of this crystal by applying a very strong field. And what you end up with now is not an oscillating structure, but it is a structure that is quasi-phase match and that will ignore, let's say, that will pass this phase here to be able to nearly follow the perfect phase matching. It's never the same, but that's a way to have a signal that is not totally annihilated after 2 coherence lengths. You can do that not only in bulk crystal, that it was done the last decades, but on lithium niobate on insulator. So you place electrodes on your lithium niobate on insulator, you apply a field, very strong, 500 volt typically, to these electrodes, and then you obtain the inversion of the domains, just the orientation of the polar axis of your crystal. This is something that you can then use e-beam lithography to make the waveguides out of this periodically poled structure. And here is just one example of the poling that we can reach at the moment, and some recent paper from one group here, how they have realized those periodic poling on lithium niobate on insulator. Okay, so why we need this kind of periodic poling on a chip? It's because we need quite some power on a chip to be able to realize those photon sources. And also here are the photon sources, because the photon you are going to generate, they are non-deterministic. And this has been done, right? In bulk, you have been able to do these periodically poling crystals. Those are papers that you can find also from the Nobel Prize of last year, how they were using that kind of sources. And now we are trying to avoid this periodic poling by using sub-wavelength structure. So we try to stay with the structure sub-coherence length here, so that you don't have the phase mismatch within your structure. But then you have to make tiny structure, and then when you make tiny structure, the signal are weak. So what we are trying to do here then is to enhance the signal either with small resonator. Here's an example of aluminum gallium arsenide single nano antenna that act as a resonator, or metasurfaces. Here an example of a lithium niobate on insulator metasurfaces that are used to enhance the parametric down conversion signal. And what we started working with is also bottom-up. So we wanted to see if we could use bottom-up nanoparticle or first microparticle to generate those spontaneous parametric down conversion signal. And we started with lithium niobate cubes. They are 2 to 3 micron in sizes that we deposited by drop casting them on a glass slide. And then we strongly illuminated this cube with our 775 nanometer pump to generate our idler and signal at typically the telecom wavelengths, 1550 nanometer. Here you see the particles, the cubes, or the wires that I will show you before. We also have a 1550 nanometer source that we can use to characterize second harmonic generation, because if we know if our particle shows strong second harmonic generation, so the invert mechanism as SPDC, we know our Hanbury-Brown twist experiment will be successful. So here we just have first measurement that we're expecting out of a very thick wafer. What we measure here is the coincidence count versus the time difference. So we measure the second order autocorrelation function, which just gives us if 2 photons are arriving simultaneously on our low temperature detector. So here we have a splitter to split those photons, and we are measuring at 0 time difference if we have a certain coincidence counts. And what it needs to be is high signal to noise ratio, so that it means we have a good rates of generating those photons from this single structure. So we measured the SPDC from this kind of cubes. We have previous work on those cubes that shows they have a main crystalline axis, which is along the diagonal of the cube. And if you measure, or if you orient the laser, polarize the laser along this long axis, you have a very strong responses of your cubes. So this is at nearly at the orientation here, you see that you have the strongest nonlinear optical responses. In blue, this is economic generation, and in red, this is spontaneous parametric data conversion for the different orientation of the light. And this is our G2 measurement. So this second order correlation function, autocorrelation function at a 0 time delay, where we expect a high signal to noise ratio. So this is really the footprint of 2-photon generation process. Right now, we just have the Hanbury-Brown twist experiment. We don't have the Hongo-Mengel experiment on those cubes, but this is the goal to do it. Here you see the photon pair counts versus the power, and SPDC, so is actually linear, where you crank up the power, which is different from seconomic generation, right? In seconomic generation, you are nonlinear with the power. So here, this linear dependency with the excitation power is really a fingerprint of SPDC as well. Okay, the structure, they were still a bit big, right? It's 4-micron structure. Therefore, we went to gallium arsenide nanowires because, as I was telling you before, the Chi2 component is very strong. It's up to 1 order of magnitude stronger than lithium niobate. For instance, here you have 370 picometer per volt components of a gallium arsenide nanowire. They are grown by MOCVD or MBE, and we just scratch them onto a substrate that is transparent and non-fluorescent so that we are able to measure spontaneous parametric down conversion. We are also using ion beam milling to cut those wires so that we make resonators out of wires that you don't necessarily control exactly the sizes. So this could be a good alternative to lithium niobate on insulator for bottom-up experiment. Then we measure along this polarization the response of the wire. You see, okay, here we are rotating the polarization, but you see we have very strong responses where you are nearly parallel to the wire, because here the main axis is parallel to the wire. And the seconomic generation is also as strong as the SPDC and the same orientation as the SPDC, so that we know how to reorient our laser. Because when you have a SPDC, we need to integrate few minutes, even few hours sometimes, which means that we cannot align live. You really have to align on the seconomic generation signal. Then on this kind of sample, we measure the correlation measurement for, again, illuminating at 780 nanometer. And we see here we have a pretty good coincidence count measure over 30 minutes here with a coherent responses with a signal to noise ratio above 2, right? It's about 50. We also have the linear dependence of the photon pairs over the power or the pump power when we increase the pump power. And what is interesting to compare is the efficiency, the conversion efficiency of microcubes, nanowires that we're also slicing. Currently, we just have the simulation of that kind of resonator, which we try to make them resonating at the pump power and the seconomic generated or the spontaneous parametric down conversion power. And if we show the size to scale, this is how it looks. And what we're expecting is that the conversion efficiency for that kind of small structure can be even higher than the one for nanowires, because they are really small resonator here. And this is what we are about to measure soon. Okay, so I was showing you example of those single particles. You're also assembling them. Right now, we don't have SPDC out of randomly assembled structure, but that's what we are working on. And the last few minutes, I'm just talking about sol gel, because you saw, right, the particles can make structure that are really rough, as you were seeing in those microsphere assemblies. And we're also looking for methods to make smooth films of solid materials that are still polycrystalline, because when you make a sol gel, even after the heating or calcination process, what you obtain is a polycrystalline ceramic. And here what you see is polycrystalline ceramic of barium titanate. What is nice is that it is smooth as compared to nanoparticle structure. So you will have less scattering. That's what you want for optics. Higher refractive index. So the effective refractive index here of particle films is much lower, so 1.8 and below, than the refractive index of sol gel, which is nearly 2. and which is still both below the refractive index of bulk material. But you're really trying to push this refractive index towards the bulk by using sol gel. And of course, you want to have to find a substrate that stands the 600-degree calcination step that we have. Okay, so here I just show you a few examples and then I conclude. So here you have an example of how we start from a silicon master mold that we do in the clean room. We prepare a mold in PDMS that we can use to really mold the barium titanate sol gel right after deposition on the substrate. So all those steps can be done in a chemistry lab, so you don't need to go to the clean room, and you can reuse the stamping, right, of the PDMS all in all, so you don't need to have each time e-beam lithography and so on. And what we can do is very precise critical dimension. Here you see 60 nanometer critical dimension of this L3 cavity in barium titanate. This is the master mold, this is the silicon mold and the imprinted cavity. And we also did some barium titanate photonic crystal, and here you see the deep of the photonic crystal. This is a transmission deep where we have a measurement of perfectly transmission deep at 775 nanometer, which is interesting also further for us for SPDC measurement. And of course, the typical second harmonic generation measurement that is quadratic with the power. So here is the pump power that is increased, and the second harmonic generation counts that is quadratic with the increasing pump power. Here you just see the linear spectrum of the pump and the second harmonic generation. And the type of material we can do is sol gel metalens as well with the same technique. Here you see the very precise shape of the fins of this metalens with high aspect ratio above 9, even 10 after the calcination steps, which is needed, right, to make metalens that will focus the light. Currently, we are just able to focus the light linearly, as you can see here. And we have a focal point here in orange that we are simulating, and what we get is in blue. And this is the objective distance, so 12.5 millimeter, the objective distance from the sample to watch this kind of focusing effect here close to our metalens. And here, this image actually was a 2-photon microscope image just to image the barium titanate fins and to see how homogeneous was our sample after the nano imprinting, and with no remaining thin films. Even though everything is wet, we are able to find the right amount of material to put for the imprinting so that we don't have films that are disturbing our measurement. Okay, to conclude, I showed you how lithium niobate insulator for top-down fabrication in integrated circuits is interesting and now rather mature fabrication process. And I also focus on bottom-up fabrication that we use first nanoparticles to make microspheres, films. We can also drop cast them around plasmonic antennas, or we can make wood pile structure. I didn't talk about that today. We also have studies of how barium titanate is in an interesting material at this kind of nano size. We are also doing not only electro-optic or thermal optic measurement, but those materials, they are also piezoelectric, so you can do a lot of electromechanical measurement. So I strongly encourage you to submit some new results to Clear Europe in Munich next week. And I like to thank you very much for your attention and thank my group as well. Thank you, and happy to take questions.